Math 30-1, we're going to look at topic 9.1, exploring rational functions using transformations. Well, some examples of rational functions are y equals 20 over x, f at x is equal to 3x squared plus 4 divided by x plus 5, or c of n is equal to 100 plus 2n divided by n. You'll notice in all three of these we have a polynomial in the numerator and in the denominator, and that's what we're going to define these as. Rational functions will have a polynomial in the numerator and the denominator, and the definition of a f at x is equal to p of x divided by q of x, where q of x cannot equal 0. Example 1. Let's examine our base function of y equals 1 over x. If we plotted some points and graphed it, if x was negative 10, 1 over negative 10 is negative 0.1. If x was negative 5, we'd end up with negative 0.2. If x was negative 1, 1 over negative 1 is negative 1. If x is negative 0.5, we'd end up with y being negative 2. And if x was negative 0.1, we're getting smaller and smaller here for x, y is going to get larger and larger. That's going to become negative 10. And if we get to x is equal to 0, 1 over 0 is of course undefined. And now we're going to go the positive direction. When x is positive 0.1, 1 divided by 0.1 is 10. 1 over 1 is 1, 1 over 5 is 0.2, and 1 over 10 is 0.1. Now if we plot these points on our graph, we're going to get a picture of what y equals 1 over x looks like. Plot some points, connect the dots, and you can see what the graph of y equals 1 over x. There we go. And now let's examine the effects that the parameter a will have on our function. From y equals a over x minus h plus k. A is called the vertical stretch. Even though it doesn't really look like a vertical stretch, it still is called that. When you graph y equals 10 over x on the same set of axes as you would y equals 1 over x, we're going to generate some points the same way we did for y equals 1 over x. And when we plot these points, they're going to get an idea of how it behaves when we times it by 10. Notice that there's still going to be a horizontal and a vertical asymptote at x equals 0 and y equals 0. It's said to have a stretch factor of a equals 10, since y can be written as a times 1 over x, or 10 times 1 over x. Both graphs have a vertical asymptote at x is equal to 0, because x is undefined at this point. And both graphs are going to have a horizontal asymptote at y equals 0. And we say that this is because, first of all, the numerator is never going to be equal to 0 because the numerator is always 1. And secondly, when we look at our stretch, or our equation, y equals a over x minus h plus k, in this one, k has a value of 0. And what you're going to notice as we work through these is that the horizontal asymptote is going to be y equals k. When we graph a rational function using transformations, we're going to graph y is equal to 6 divided by x minus 2 minus 3. So what we're going to do is we're going to start out with our base graph of y equals 1 over x, If we multiply it by 6, we're going to get y is equal to 6 over x. And then if we applied our horizontal and vertical stretches, our horizontal and vertical shifts, we're going to get 6 over x minus 2 minus 3. Our base function, we're going to apply a vertical stretch of 6, a horizontal shift of 2 units to the right, followed by the vertical shift of 3 units down. So there's going to be a vertical asymptote at x is equal to h. Here it's going to be at x is equal to 2. And there's going to be a horizontal asymptote at y is equal to k. And here, y is equal to k means it's going to be at negative 3. From y is equal to a over x minus h plus k, you can see how those two values fit into our equation. To draw the graph, this is what it's going to look like in its final form. The graph in blue is going to be y is 1 over x. When you apply the vertical stretch of 6, you're going to get the red graph. And then when you apply the horizontal and the vertical shift, it's going to move 2 units to the right and 3 units down. So that means that our asymptotes, instead of being at x equals 0, is going to shift to x equals 2. And our horizontal asymptote is going to shift from y equals 0 to y equals negative 3. Now if I was drawing this graph from scratch, I would draw in my axes, then I would draw in my asymptotes. I'd put in a vertical asymptote at x equals 2, and then I would draw in my horizontal asymptote at y is equal to negative 3, and then I would draw my graph to fit my asymptotes. So there I have my graph of y equals 6 over x minus 2 minus 3. Alright, in example 3, we're going to graph another rational function. This time, it's going to have a linear graph divided by another linear graph. Well, this time we've got something else happening. And there's another rule that we're going to have to follow. And that is, to find our vertical asymptote, you have to find where the denominator is equal to 0. That's going to be the same. That's going to be at x is equal to 2. Drawing that in. To find the horizontal asymptote, here is the rule. If the degree of the numerator is equal to the degree of the denominator, which it is, they're both degree 1, then what we're going to do is we're going to say from our base ax plus b over cx plus d, there will be a horizontal asymptote at a over c. A and c are the leading coefficients, and here that's going to be at 4 over 1. So we're going to have then a horizontal asymptote at 4. Drawing that in and drawing in some test points, you're going to see that we're going to get several points, and as we draw them in, we can plot them. And that's what our graph's going to look like. There is a vertical asymptote at x equals 2, the undefined value. There's a horizontal asymptote at 4 over 1, which are the two leading coefficients. But this only works when the degree of the numerator is the same as the degree of the denominator. You have to keep that in mind. Here we go in example 4. We're going to consider functions f at x is 1 over x squared. G of x is 3 over x squared minus 10x plus 25. H of x is 6 minus 1 over x plus 4 all squared. They want us to graph pairs of functions. In the first graph, we're going to graph f at x and g of x. Well, if we graphed our first function, 1 over x squared, it's what it's going to look like. Now, if we look at the second function, g of x is equal to 3 over x squared minus 10x plus 25, I notice that the polynomial in the denominator can be factored. So we're going to express that as 3 over x minus 5 all squared. So right away that tells me that it's not going to be defined at x is equal to 5. So I am going to have a vertical asymptote at x equals 5. Also tells me that I can factor 3 out of this function. I'm going to keep the 3 out front. Now I can write it as 1 over x minus 5 squared. And now I can relate the two functions. I can say g of x is just 3 times f at x, but the whole thing is going to be shifted now 5 units, and that's going to be 5 units to the right. So when I draw my asymptote in red, as you see there, now there's going to be a stretch of 3, and there's going to be a shift of 5 units to the right. So there's our graph in red of 3 over x squared minus 10x plus 25. Let's look at our second pair of functions. Again, we're going to draw in our f at x is equal to 1 over x squared. Let's look at h of x. Well, first of all, let me rewrite this the other way. Let me write it as negative 1 over x plus 4 squared plus 6. Now if you notice, this is going to now be the negative of 1 over x plus 4 squared. So it tells me it's going to be flipped over the x-axis and be in the negative. Also tells me that there's a plus 6. The whole thing's going to be shifted up 6 units. So when I examine this, I'm going to get a horizontal asymptote at x is 6. I'm going to get a vertical asymptote where this is undefined at x is negative 4. And I'm going to get it flipped and be in the x in the negative x values. So first of all, again, writing this in terms of our original function, I've got the negative of f of x. There is no stretch, so it's just going to be the negative of f of x plus 4, meaning 4 units to the left, and shifting it 6 units up. So if I plot some points now, what you're going to see, well, here's just writing that out. Negative flipped over the x-axis, horizontal asymptote, y is equal to 6, and a vertical asymptote at x equals negative 4. And if you draw those in, there is our asymptote for a vertical asymptote. Here's our horizontal asymptote. And now when I draw my values in, all on the negative side, so everything will be below 6, that's what it's going to look like. There we go. Again, we have h of x in purple, f of x in black, and g of x in red.